The square-wheeled car. This is Math 4250 at the University of Georgia, and I'm Professor Jason Canarella. In this video, we're going to think about the problem of a square wheel rolling along a rounded road. Now this road is almost flat, and we've slowed down the video to show you that as the contact point between the square and the road gets towards the end, the axle of the square gets lifted far into the air. Here's the video at a normal speed. We can see what's happening a little better if we draw in the curve traced out by the center of the square. You can see from the arches at the left and the right that the center of the square is lifted far above its initial position at the origin. Our conclusion is that this road is too flat. It doesn't leave enough space for the axle to descend into at the ends of the rotation. So let's try something with more of an arch to it. As we can quickly see, this doesn't work either. The ends now bend down too steeply, and the center of the square drops below the axis, something which we can see even more clearly if we draw this in as a curve. In an attempt to split the difference, we'll try an arc of a perfect circle. This looks surprisingly good, but when we zoom in, we can see that the center of the square isn't quite tracking along the x-axis. It still rises just a bit at the ends. This last shape is exactly perfect. The arch changes just enough to keep the axis exactly on the center line. Even zooming in confirms that we've got it right this time. The center of the square glides right along the x-axis. Now that we've seen some visual evidence that this curve exists, let's talk about how we can derive it. In this picture, we're keeping track of 4 points as the square rotates. O is the origin. It's at the intersection of the two axes. It's connected to P, the contact point, where the square touches the curve. There's a vector from there to Q, the midpoint of the lower edge of the square. And Q, of course, is connected to C, the center of the square. Pausing here, we can see some geometric relationships. P of S is a point on the curve. Q follows the edge of the square back from P to the center. And of course, the edge of the square from P to Q is perpendicular to the line from Q to C. In your homework, you'll use these relationships to derive an equation for the path C of S in terms of the shape of the arch, x of s comma y of s. From there, you'll be able to derive a differential equation for the shape of the arch which keeps the y-coordinate of C of s equal to 0. That's exactly the road we need to make our square roll smoothly. We'll now let the whole apparatus rock back and forth a few times to help you develop your intuition. After that, you should go ahead and start working on your homework. Have fun!